Welcome. In this session in linear data analysis, we'll explore training and testing, which is the introduction to cross-validation for linear regression. Let's define some terms. Let's define training as using data to find our W. And then let's define testing as evaluating the model using our weight vector W. In the context of linear regression, what we did, so previously, let's recall this, previously what we did was we used all of the design matrix and y vector to find our W, and then we used all of the data to evaluate. And this is referred to as validation. So when we do this, we're using all of the data, and you can see that there might be a little bit of a methodological problem here, which is if you've used all of your data to find the weight vector, how do you know how well the model will perform on new data? Because that is one big part of machine learning, right? We don't want to just find a model, we want to use the model. And so what can we do? Let's consider using sum of x and y to find W. And then let's consider using sum to evaluate, in this case, the model. Well, what's the simplest way that we could do this? Well, what we could do is we could leave one out. So what we could do is we could hold back. So the idea behind leave one out is this. So we could, for example, we could hold back. This is a term that's sometimes used. We could hold back the first observation and the first set of independent data and the first set of dependent data. And then we could train on the remaining so this would be xj, yj for j greater than 1. So we could do that training, and then we could test on the holdback. So we could test on x1, y1. And this gives us one prediction. So could we do this again and again and again? Well, I don't see why not. So we could hold back Let's suppose we hold back xi, yi, and then we train on xj, yj for j not equal to I, and then we test on our holdback xi, yi. So this gives us, how much does this give us? Well, this gives us train and a test for every row of our X matrix, that is, for every observation. So this gives us M predictions. And from that, we can find statistics. Find statistics of our strategy. Now, let's think about how much time is this going to take us? Well, let's think about the computational complexity. So the complexity is M times on M minus 1 data, and we would represent that using big O notation as M squared. Well, okay, so it's going to take us a quadratic amount of time. Well, if we have 100 data vectors, that's not a big deal. But if we're doing something which is the result of a web search, that M might be millions. And if we have millions, then millions times millions, we're dealing with trillions, and suddenly, even in a simple leave one out strategy, we may be facing a computational complexity problem. And it gets worse, is that if we say for leave L out, this means we have to repeat it. Well, let's see, what does leave 2 out do? Well, that would be, we would pick X1, and then we would test it against, its second pair would be X2, X3, X4, and so on. So that means that for each one of these, for M, we would have M minus 1, and then we would have M minus 2 data, so we would have a cubic problem. And then the trouble is, if we leave L out, as we increase the robustness of our test, what we're doing is we're repeating this M choose L times. And as we do that, it becomes computationally infeasible. So let's make an observation. And this observation is one that we can only make, we can't really support in linear data analysis. We need to go to statistics. This observation is, this detects what we call singleton, or let's say single statistical outliers. That is, if there's one data observation that has a problem, it will show up as having a very high test error. But if there are, say, 5 out of 1,000, if we're dealing with a small data set that only has 1,000 observations, then if 5 of them are statistically unusual, we may not be able to detect that. So we would need a more robust measure. So this detects single statistical outliers. And the problem is, now, we have a basic strategy. The basic strategy is we'll train using one part of the data and we'll test using another part of the data. Now the question is, can we do that in a computationally feasible and cleverer way?